we are now going to spend 2 weeks talking about one phenomenon and ordinary wall outlet electricity. 2 weeks on this module. It's short, but my goal is to do something, hopefully you will find interesting, practical, real world, show you how electricity is generated, really. And that will also lead nicely into what we were doing for our last module, oscillations and waves. Oscillations and waves, optics, sound, all that stuff is very common for MCAT, by the way. And not OCAT, for God's sake, what do the optometrists take? The optometry test, what's that? OAT. OAT uses the wave stuff too, the light stuff too. So that's my plan for the rest of the semester. This week, I have one equation really to teach, but don't get complacent. It may only be a couple of symbols, but this has wrecked people who underestimated it. This is the opposite of the last module. Last module, there were a butt ton of equations, and each of them individually were fairly simple. Now there's one equation that we're aiming towards, but he's a beast. We're going to do a deep dive into the equation today, and next time we're going to talk about the direction of the equation. Magnitude today, direction next time. Okay. All right, so here we go. Let's dive in. Induction, by the way, yeah. I am, thank you. Induction, last, when we talk about static electricity, there's charging by induction. This ain't that. Electromagnetic induction, charging by induction, reasoning by induction in math class, 3 different topics. So don't get this confused. I must start talking about EM induction by talking about one of the phenomena related to it. I said that this is one equation. It's one equation that explains lots of different kinds of stuff. I want to start with one of the kinds of stuff, moving a piece of metal in a magnetic field, that you can already calculate without the hard formula that we're developing, okay? So we're going to come up with this, and then I'm going to show you, I'm going to turn that into, I'm going to let it evolve to its final form. Is that what you guys say in Pokemon, right? Now let it take its final form, and then be using that for everything. If you wave a metal rod in a magnetic field, there is a voltage across it. Magnetism is not electricity. I hope I beat that into you guys. But magnetism can be used in certain circumstances to drive electricity. So, if you wave a conductor around, Earth's magnetic field, really kind of weak. You would have to move a big rod really fast to be noticing this with our 52 micro Tesla field. We will do in lab stuff that you can see this very easily stuff next week. Here's the origin of this this voltage that you could use to drive a current even. The magnetic force on the moving charges, remember the magnetic force formula, QVB? That magnetic force pushes the pluses and the minuses in opposite direction. Remember, if you flip Q, you flip the force. Deja vu? Okay, QVB pushes the different charges in opposite directions. That builds up, it builds up, it builds up, pushes harder and harder and harder, until if you got a solid piece of metal, that flow only stops, only comes to an equilibrium when the electrical attraction between the plus and minus is balancing the magnetic, driving them apart. Well, hold on, magnetic force and electric force being equal, you know the electric and magnetic forces. What are they? What's the electric formula? Force in terms of field. QE. I think I heard. Forces, charge times electric field. What's the magnetic force formula? Just said it. QVB, precisamente. So we get a balance, the electrical flow in a single solid object stops when QE equals QVB. Well, okay, hold on a second. I was talking about voltage before, and I'm talking about field now. You know the field equation, QE. I want to turn this into, use the voltage relationship to turn it into voltage because electric fields are hard to measure and voltmeters cost a couple of bucks. But we're going to see in lab, and it's just more observable. What's the voltage field relationship? How do you get field from voltage? You remember that from last chapter? How quickly it flies. Not U. I want V and E. There is a delta. Huh? Q delta V. Q delta V is energy. You want to take a step? V equals ED. Good, good, good. Or we could say E is volts divided by meter. Deja vu? Volts per meter, voltage divided by distance gives you electric field. It's another way of picturing electric field. VED. You need it for the final, don't forget it completely. Okay, so we're going to use that. We're going to turn electric field, which is hard to measure, into volts per meter, then solve for voltage. Uh-oh. Watch out. Voltage. What letter do we use? What letter do we use for speed in the magnetic field? Uh-oh. Watch out, my friends. Watch out. Do not use V and V in the wrong way. One V is voltage, one V is velocity. Okay, watch out. Now I'm going to give, it is a tradition to give an example where we have this voltage used like a battery. The traditional example is I'm going to make an electric circuit out of a U-shaped piece of metal. Here, my two arms and my torso are a U-shaped piece of metal. Then I'm going to let a barbell slide down my arms and bonk me in the head. That's the circuit. If you have a magnetic field near the moving barbell, the magnetic field will drive a current. It generates a voltage. I'll sketch this. I'll sketch the silly example. It's silly, but it's also in every textbook ever that talks about electromagnetic induction. They always use this example. So we say we've got a rod and a U-shaped piece of metal, a conducting channel. And the rod is allowed to slide up and down, but it's selectively in contact. It makes metal-metal contact. You can have a current flowing through this. It's a complete circuit. Well, complete circuit, where's the battery? Where's the resistors? Where's the capacitors? You don't need them. We could still have a complete circuit as long as there is a complete path for electricity to flow. But how the hell is electricity going to flow with no battery? The magnetic field provides the battery. That's this chapter. We're going to see how magnetism can create electricity. Okay. So got a U-shaped wire, a bar which is allowed to move up and down. We're going to analyze this. The traditional letters to use are L for the length of the bar. Ooh, super mysterious, that one. And we're going to talk about the height of the bar. And I'm going to say that the height starts at H, and then we're going to later write an equation for how the height changes. Watch out. So far, so good? We're going to use this setup to discover the master equation that applies to phenomena even with no motion. Everyone got this drawn? We're going to use this several times. Okay, we're going to combine those expressions. I want to get a simple equation. If I say QVB equals QE, that's E equals VB. Yeah, I can divide both sides by Q. So the electric field that balances in a simple piece of moving rod, the electric field inside the rod, it better balance the magnetic force, VB. if I plug in electric field as voltage per meter, I get voltage equals length of the bar times velocity of the bar times magnetic field of the bar. But magnetic field of the bar is in LVB. If we're just doing motional EMF, that's it. You can multiply three numbers, God willing. You're going to multiply three numbers and you're done. Motional EMF, super easy. But this is part of a more sophisticated thing that explains lots of things. That's where we're going. Okay, so let's take a second. Multiply three numbers for me. Apply the equation you just learned. Tell me the voltage that happens when I take a 32 centimeter piece of metal in a big honkin' 0.42 Tesla magnetic field and move it at 6 meters per second. Google form A. Let me see how you do. This is a big magnetic field, by the way. You need a lab-sized magnet to do this, or a bunch of really strong solid magnets. Good, K-Sprang. Good, T-Hammam. Watch the units, my friends. If you measure volts in. Good, EH-tran 2. Yep. So you can actually melt them out. That's what you think. 30 to 70 will be great mix of these two. One mixed what is 0.42 on the one for the second. It's not exactly, but it rounds to that. Hey, my friends, use the formula that I just delivered to you, LVB, VLB, and watch your units. Make sure to convert what a centimeter is. How to remember what a centimeter is. If you got 32 cents, how many dollars have you got? $0.32, yeah? Cents in a dollar, centimeters in a meter, same thing. All right, lots of correct answers. I love it. Is good? Is happy? And again, I want you to know the meaning of this. It's not about memorizing formulas. It's about having ideas, how to understand ideas. What is magnetic? What are we saying? Motional EMF is the name of this. Magnetism can be used to push charges inside a piece of metal around. If you wave a piece of metal, a solid piece of metal can get a magnetic push You could use that energy contained in the magnetic field to drive a voltage, maybe to drive a current if you've got a complete circuit. And the formula for this BLV, we're going to apply this and make this more sophisticated in just a second. Don't get scared. I'm going to do this turn by turn, line by line, inch by inch, centimeter by centimeter. BLD. Let's just drop the B for a second. We're going to have constant B. Let's just look at length times velocity. The length, what's the length? The length of what? In our example. The length of the rod. What's V? The speed of what? The speed that is going, very importantly, up and down. Which direction is the rod? Left, right, horizontal. Which direction is the motion? Up, down. Remember from right-hand rule from before, you got to have right angles between stuff or magnetism does squat. I'm going to give you a couple of exceptions that we'll talk about later, and it ultimately goes back to, for most of them, you've got to have right angles between your field, your velocity, your length. Otherwise, you don't have a magnetic effect because you'd be costing. Okay, so length times velocity, muy importante, they are at right angles to each other. Hey, what's velocity even? What's the equation for velocity? It was like the first thing I told you last semester about velocity. Displacement divided by time. Delta position. I guess in this case, we were talking about position as height. I want to write height as h. You okay with that? Position is h, delta h over delta t. Everyone comfortable with h being position? Remember, capital H, starting position. Little h as a function can be any position at some time. So this ain't nothing but the meaning of velocity. Okay, now, hold on. What does delta always mean? Change. What's the formula for delta foo? Final foo minus initial foo. So delta height is the final height minus the initial height. Let's write that expression out. L times puff minus high. High. Can I rewrite this mathematics in a different way? If I multiply a subtraction, what happens? Follow along. Trust me, I'm going to lead you somewhere. What happens if I multiply two things that are subtracted or added by one number? They both multiply inside. I can rewrite this. I can re-express this. I'm going to get there. I can re-express this as L times HF minus L times HI. Okay, yeah, for real? LHF minus LHI, that's just the change in the quantity LHF. The change in the quantity LH, right? Length is not changing. Height is changing. But I could say length times height is changing. Good. Okay. What's length times height in this rectangular scenario? Area. So length times velocity has a meaning. It is the rate of change, the slope of the area. We can write a formula for the area as it changes and say how rapidly is that changing. That is the area per time, the rate of change of area. We spent 6 weeks on rate of change in the first semester, coming back with a vengeance. You guys need to remember that delta over delta t means slope. As if you graph something versus time, and you should be able to identify if I've got an equation, say 2 plus 3t. What's the slope of 2 plus 3t? Ooh, that should be faster. What's the slope of 2 plus 3t? Show me with your fingers. Everyone give me the finger. Slope of 2 plus 3t. Google form B, real fast. 2 plus 3t. Y equals 2 plus 3t. What is the slope of this function? Come on, chop, chop, fast, 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 fast. Google form B. I give you the equation. Y equals 2 plus 3t. What is his slope? Okay, thank God. Good. Please. Good. How do you know it's 3? Did you have to use your calculator in a formula? I don't. What I do internally is I look at the slope is whatever multiplies your independent variable. Yeah? Okay, we're going to use that in a second. This is LV. Is the formula voltage is LV? No. What's the formula? BLV, right? So I've got voltage is B times the rate of change of whatever the heck the area is. Well, hold up. I just played a trick that said I could pull L inside V, inside the change, and interpret that quantity. I'm going to do the exact same thing. V times delta A is going to become delta BA. Do you guys believe me? If I have change in area, final minus initial, I can just multiply B on each of those, and I get BA final minus BA initial. No, you don't believe me. I'll write it out. If I have B, oh, for God's sake, B times the rate, let's just look at the top, change of area. That is to say, if I've got B times area final minus area initial, can I not say that this is just BAF minus by? By? That's nothing but the change of the quantity BA. Okay, what is magnetic field times area, everyone? What does that mean? What does that feel like? What does that taste like? You shouldn't know. It's a new idea here. Length times width, you guys learned that in what? 3rd grade? Magnetic field times area, that's a new quantity. We're going to call that flux. Okay, so I am going to play the same trick that I did before. I'm going to pull the constant inside the change operation, constant inside the delta, and then say BA is a new quantity called flux. What the flux? Muy importante. Magnetic field has a direction. Area is directed. The area must be pierced by the magnetic field direction. If I've got a loop around my hand, like this, if I attach a piece of wire around my hand in this plane, my hand is the plane of the area. If the magnetic field goes into my hand, like this, it is piercing the plane of the loop. That's got B times A flux. If you've got wire wound in this, and the magnetic field is coming in parallel to that, what do we know about parallel magnetic whatever? 0. There's no flux in that case. So B times A, you have to care about which direction magnetic field is. Is it going through the area? Much more on this next one. Okie? So here is a new variable I am introducing. You must be able to describe and define, well, to define this, to give the equation. Magnetic field phi, magnetic flux phi is field times area. Question, Harsh?
So, the second last format, how did we put D inside the change?
Change is just final minus initial.
Yeah.
Final minus initial times B is B final minus B initial, yeah? Well, I just defined B final is a quantity. Its final value, B area, B flux final. B area initial is just, I call that initial flux. So I'm just evolving BA into its own variable and saying that variable's final value minus that variable's initial value. So far, so okay? You guys don't know why I'm doing any of this. You got to be trusting me that this is going somewhere. But so far, it's just algebraic, really just arithmetic. 2 times 3 plus 4 is 2 times 3 plus 2 times 4. That's the only math we've done so far. And I'm defining a new quantity that I claim is going to be important. Okay, but it is the 4:30 section, which is always brutal to brain in the afternoon, late afternoon. Please turn to each other and tell each other what we've done so far. It's not a long story, but you need to be able to do it. Ready, set, go. Okay, let's bring it back together. Give me a question. I hunger for questions. I have a question vampire. Such a questions out. Give me a question. No? Actually making sense? Please.
Similar to not the same.
Field is not actually a thing that moves. Magnetic field isn't actually a thing that is flowing. It's kind of, you can visualize it like water flowing around the river, whatever. But field, magnetic field is nothing actually moving. Magnetic field does not move. It can cause motion.
But
That doesn't mean it is moving.
the motion causes nothing to do. Magnetic field.
Flux itself is not a force. Flux itself is not a current. Flux itself most certainly is not motion itself. If you want an analogy for how to think about flux, let me actually go back to what you were talking about a second ago. If you've got water swirling around a river or lake or whatever, we can call the magnetic field is just the direction and speed of the water. You know, if you've got little eddies, maybe a whirlpool, water's going faster here by the shore, it goes slower. You can talk about the velocity as the strength, the direction is the direction of every point. Flux is, you put a hula hoop in the water here, there, everywhere. Flux is how rapidly the total amount of water is passing through that. How many gallons per second are going through that hoop?
So it is an amount.
It's an amount, but it's an amount of not a thing which is moving, but an amount of magnetic field. It's a total magnetic oomph. Did y'all hear that, by the way? You listen when other people ask questions? Some of you, anyway. Some of the time. Some of the days. Okay, write this down, circle this, square this, star this. This is Faraday's law. Called Faraday's law. Remember the farad, the unit of capacitance? Same guy. Michael Faraday. We're going to apply this to several different contexts. This is an amount, right? A magnitude. The direction is going to be the entire subject of tomorrow. Oh, class tomorrow, of Wednesday. I'll give you a preview of that if we get through this lesson in a decent amount of time. Give you a preview at the end, but direction, sorry. Okay. 5, I just gave an analogy for how to think about it. Total magnetic oomph, total amount of magnetic field flowing through an area, even though it's not something that actually flows. I still have bunches of students ask me, well, how do you get phi? How do you calculate it? Give me a way to get the equation. I want to do that next, but first, Harsh.
I had a question, so while we were deriving magnetic flux, we talked about velocity, and then we went to the formula of the velocity, which is displacement by time. So when the rod is at a zero displacement, what will be the scenario?
Actually, the amount of flux itself doesn't matter as long as it's changing. You don't care about what the flux is, you care about the rate of change. Does delta position over delta time stop if you are at position zero? No. As long as you are moving, you can move through position zero. Do you not have an acceleration at the moment you turn around at the highest point? As long as your velocity is changing, you still have an acceleration. You will always have an induced voltage anytime flux is changing, even if there is no flux at that instant. Good. Okay. Let's calculate a phi and let's practice a little algebra. So far, all we've done is really the distributive law of arithmetic. Let's do a little algebra and get deeper in this. I'm going to do the same darn example. I'm just going to do it in a different way. Okay, so same scenario as before, right? You got the U-shaped piece of wire. We've got a rod moving down, touching it, or up, doesn't matter, moving along the conducting channel in the magnetic field. Okay, yeah, right? Everyone happy with that? Let's write a formula for flux. What's the flux equation? I want a formula for flux. So what's flux? Define it. BA. That's a true statement, but it's not the definition of flux. Here's how you get voltage out of this. First, you have to know the defining equation, the always true statement is flux is BA. Okay? So far? Yeah, right? What's magnetic field in this problem? Oh, it's just given. I could plug in a number if I wanted. As the rod is, let's say, dragged up the channels, dragged up the rails, is the area of that rectangle constant or is it changing? Is that area constant or is it changing? It's changing. First, you got a small rectangle, then you got a bigger. So I don't have a single number I can plug in for A. I have to write an equation. What is the equation for area of a rectangle? Length times height? Well, I've got length, right? I gave you length, 32 centimeters, 0.32 meters. I could just write that out. But now I need to write a formula for height. Turn to each other and see if you can write down an equation for where this thing is as time passes. Put this in Google Form C. Let me see what you can do. Let's say this thing starts on the ground, like Harsh was asking. This thing starts at h equals 0 and moves up at the speed shown. Okay, turn to each other. Google Form C. Give me just an equation for height as a function of time, h of t. Height equation. Do you know what you're doing? You know what I'm asking? Go do it. How many meters tall is this sucker? Give me an equation for it. Are you guck? No? You guys don't remember this? No like make equation? Okay, let me remind you, the defining equation for velocity that we just wrote down, whoa, is change in position versus time. is the meaning of velocity. I give you velocity, right? I want an equation involving position in terms of givens and time. I want an equation with time as a variable. So I could multiply both sides by time. And I could interpret what position am I talking about? I'm talking about the height. Let me write that more nicely. Okay. Yeah. So what's the equation for height as a function of time? 6 times time. That's if you start at ground height. What if I started at 1 meter high? What if height initial were 1? 6t plus 1. What if I started at 3 meters high? What would the equation be? No. Google form D. Google form D. If I start 3 meters tall, wow, that's a tall rod, whatever. If I start 3 meters high and move at 6 meters per second, give me the formula for height as a function of time. I've given you 90% of it here. I start at 3 meters high. I'm moving at 6 meters per second. You should be able to tell me a formula for the position as a function of time. Good, good, good so far. Not looking for a number, my friends. If you start at 3 meters tall and are moving at 6 meters per second, you can write an equation for where you are. I'm looking for an equation. You can write a formula. It's not a number. What's delta mean? What's initial height? Can you solve for h? Hint, 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 hint. Okay, I solved this equation for h as follows. I add 3 to both sides. My final equation is h equals 3 plus, oh, what's v? I feel like this was more mysterious than it should be at this point. Please turn to your neighbor and walk through how we got this. If you start 3 meters tall and are moving at 6 meters per second, please discuss how you get 3 plus 6t. I'm assuming the arms go asleep.
It cannot be.
It starts from very tall compared to how long it's been.
Like, I'm asking like, if and the third second, it was the fully interprets. The fourth second you come back, but this question will take it further.
That's correct. We would have a piece size one. If motion has changing direction, we can't describe that. First I saw you up and I see down.
The velocity will change.
These ones. Okay, talk to me. Talk to me. Am I misreading sleepiness for confusion? Okay, let's move on. We have come up with an equation. I have made up the 3, of course, But actually, we'll see it doesn't matter. We could have anything. We can have, as I originally stated, capital H initial position. Hey, what's 42 times 32, by the way? Someone with a calculator real fast. Thanks. Any initial position. Yeah. Right? I'm just plugging in numbers and the formula we just got. Any initial position for height can have that. So the flux as a function of time. Well, hold on. I can multiply that 0.134 in. Flux equation. What's 0.134 times? Oh, it's 0.806. Height is wherever you start. Doesn't actually matter in this equation. Time is time. My last question for you, let's practice some algebra question here, is what's the slope of this line? If I were to graph phi versus time, can you find its slope? Because that's what voltage is, it's the slope of phi. Here's our goal, find its slope. Yeah, Google form E, what is the slope of this equation? If I graph this versus time, please don't use your calculator. Consider what variable is changing if I graph phi versus time. The initial height. I gave an example of first 0, then 1, then 3, but it could be anything. It's not going to change the equation
Why is it
because the height of the rod is wherever it starts plus 6t. So in general, I gave 3 different examples. My point is it can be any initial position. I'm going to make a deal about this in a second. Again, your challenge for Google question E is find the slope. If this changes as time progresses, I graph this phi versus t, what would the slope of this be? Because that's what voltage is. That's our core equation. I've got 2 letters. Oh God, what do I do? What variable is varying? Is height changing? Is initial height a different number as time goes by? Is time changing as time goes by? Time doesn't change as time goes by. It does. If I'm graphing time on the horizontal axis, what is x? This is your x-axis. This is your y-axis. How do I get the slope? I've got a number plus another number times x. What's the slope here? It's what multiplies your independent variable. The slope is 0.806. Oh my God, that's the answer to the problem. What's the voltage? Remember the voltage for the previous part? Voltage is the rate of change of phi. We found an equation for phi. Here's its rate of change. Good, good. I'm dragging you through a little bit of algebra because we need a little bit of algebra for this. You're not going to need all this algebra every time, but you do need to remember what a slope is and how to find it. You do need to remember the concepts of algebraic manipulation. This is going to be important. So no, it's not gonna be this hard. It'll be harder, no. This is not the part that I'm going to. Please review this. If you can't find the slope of a line, you need to be able to do that for this. But if you are exhausted and wondering if it's always going to be this hard for everything you do, no. Okay. No, I had one last point to make about this, why I included the H here in the first place. Harsh. Does it matter what your initial value is at time 0? If H is 0, if you start from ground height, there is no flux, right? If you start at H equals 0, then at time 0, there is 0 flux, right? 0, 0. If you have 0 flux, does that mean you have no voltage? No, as long as flux is changing with time. Just passing through 0 does not mean you don't have a slope. A line can pass through 0 and have a slope. A flux can instantaneously be 0 and still be changing, causing a voltage to be induced. Okay, that is our algebra for the day. I've got a little squishy bit more, a bit more. I want to emphasize real briefly, I'm going to say this part. I suspect that it would be beneficial to let you guys go a smidge early, at least the majority of you, and then those of you who have the mental, emotional, physical energy, stick around. I'm going to say this part. If you've got a voltage induced, and there's a whole loop of wire, V equals IR gives you the current induced. You believe that? Is that kind of duh? The moving rod acts like a battery with voltage delta phi over delta T. And then you can use that in V equals IR if I give you the resistance of the wire. Med school students, write this down. Everybody else, you don't need to care about this. I will not test everybody on this, but med school students, you'll see this reference. A Weber is the SI unit for a Tesla meter squared. B times A Teslas times square meters. There's a name for that. It could be the same. That's the Weber. Med school students, you'll see, may see this on MCAT. Everybody else ignore. Okay. B times A. Concept. B times A. What happens if area changes like we've just been doing? There's a voltage. What happens if field changes and everything is still? There's still a change in voltage. This is a different physics phenomenon. This is not motional EMF. If area is constant and B is changing only, there's no motion, but there's still an induced voltage. Any time flux B times A changes, there will be an induced voltage. Here's the magic of this. We deduced this law from one phenomenon, but this applies to 3 different things in real life. We're not using trig in this class whenever I can avoid it. With waves, we'll have to, but I have cut the trig as far to the bone as I can. But you will be tested on the idea that if the angle between the flux, for God's sake, between the field and the area changes, that also changes B, because less of the B is going into that area. It's skimming the surface instead of piercing the loop. If you've got a river and you put if you put the hula hoop sideways to the current, there's the water going through the hula hoop. So flux can change 3 different ways. B times area can change if B changes, if area changes, or the angle between them changes. We've been focusing a lot on what flux is. I do want to emphasize one last thing, another test question here. Voltage is not the change in flux. Voltage is the rate of change of flux. If time is twice as big, If the downstairs of phi over t, delta phi over delta t gets twice as big, what happens to voltage? If you double the downstairs, the fraction gets half as big. What if I took a magnet and I moved it into a loop 3 times as fast? It took 1/3 of the time. What would happen to the voltage? Increase by 3. I would triple the voltage. If the downstairs gets 1/3 as great, the fraction gets 3 times as great. What if I really shoved a magnet into a loop 10 times faster, 1/10 of the time? What would that do to the voltage? Voltage would go up by a factor of 10. Good. I'll take it. Who's tired? Okay, doctors, put your hands down. You need to get really good at this. If you are exhausted, get out of here. Please go fast. I love you, but you are exhausted. You are excused. I want to preview Lenz's law. But if you're not mentally here, there's no point. We will cover this on Wednesday, but I want everyone who can, and also my the MCAT students, to see this twice. Go fast, go fast. I love you, but go. The magnitude equation. Flux over time, or change of flux over change in time. That's the voltage magnitude. The voltage has a direction. You can put a battery forward or backward in a circuit, one side on top, both side on bottom. And that makes a difference with how the current flows. The magnitude delta phi over delta t is up to more or less straightforward. Once you understand what phi means. The direction is a 4-step process. That's why I have you here. You got the mental energy and or have to have the mental energy because MCAT. These 4 steps, it's good for you to see them multiple times. Step 1. Find the direction, right step? I'm going to say this in a very short phrase on the slides, but I want you to write this down. Find the direction of the original flux. Step 2. Step 2. Is that flux getting bigger or smaller? Step 3. The reaction flux, I'm going to call reaction flux, the reaction field, opposes that change. That screwed a bunch of students up in my 3 o'clock. We can do an example or 10. Suppose your flux is leftward, okay? Everyone visualize the flux that's leftward and getting stronger. I'm left and I'm lefter and I'm leftist. How do I oppose a leftering flux? I would push in the rightward direction. What if I've got a left flux that is weakening? How do I oppose that change? More left, okay? Does that feel okay? What if I've got an up flux that's decreasing? It's up, but it's less up. How do I oppose the change? Up. I oppose the decrease by pushing, by trying to replace some of the up that's being lost. Harsh.
Are we opposing the direction or the?
Nope. We're opposing the change. So the direction is the direction of the original field. But we care about how that direction, how that is changing as time passes. The change of intensity in a given direction. You have to know about step 1, find the direction. Step 2, find the change in intensity. Jake.
And you'll always add flux to oppose it, you will never take away to oppose it.
You don't oppose it, you oppose the change. if you are losing flux in a given direction, the reaction is to support the original, same direction. If you're gaining flux, the reaction opposes that gain, points in the opposite direction.
But you're never gonna like one more because you're not gonna hit inside, it's gonna be more here.
That might be worth writing down if the opposes the change is weirding you out. If the flux is getting stronger, reaction is in the opposite direction. If flux is getting weaker, reaction flux is in the same as the original direction. So if you don't like opposes the direction of the change, you would just say same direction if decreasing, opposite direction if increasing. Please.
I was gonna say, would it be easier, because you're saying it's the direction, so you just look at the sign, if it's negative and it gets more negative, then you just add a positive and vice versa.
Perfect.
Okay.
Racism. Do you feel okay with this? This was really screwing with heads last class. You guys, yeah,
I think the steps like.
Yeah.
that's my goal. You're the smarter class, maybe just you. Okay, that's 3 steps. The 4th step is work backwards from knowing the direction of the reaction flux to find the direction of the reaction, the induced current. You don't know how to find the direction of field given a current. We're going to talk about that next class. We didn't already do this as well. If you work backwards, we'll use the right-hand rule to show how to find the current that makes the flux you want. And that's the direction of the induced current.
So I said working backwards is just to get the induced flux via reaction flux, or?
No, you already found the reaction flux.
Okay.
No, the induced flux, the reaction flux, same thing.
Okay,
Find the current that
Okay.
makes that reaction.
okay.
One more time, all together. Find the original direction of the flux. Step 2, find how that is changing. Oppose the change, the reaction, the induced flux opposes that change. Step 4, work backwards to find the direction of current that would make your desired reaction, your desired induced flux. We could put this together in a single sentence. You look this up on Google, Wikipedia, whatever, it'll say something like this. The induced current's magnetic field opposes the change in the flux that induced it. Pick this apart. This actually is telling you the things. Look, the flux that induced it. Hey, what was step 1? Find the flux to start with, right? Step 2 was find how that is changing, right? The flux that induced it and how that is changing. Step 3 was what? The reaction field is going which direction? Opposes the change. And step 4 is what? The current, the induced current, that guy's magnetic field, that guy's magnetic flux is whatever direction opposes the change in the original. So you could write down and memorize this statement, but I like my 4-step method. It's all here. But this is what you got to do to break down. Okay, this is called, by the way, Lenz's law, L-E-N-Z, Lenz's law. You may see references to this on MCAT, my future doctors. Magnitude, delta pi over delta t, Faraday. Lenz, direction.
Is that related to like?
Nope. This is a guy. Or maybe a girl. I don't know, actually. Physics has been pretty damn sexist, but not now. Actually, you go to the labs, the national labs now, there are a lot of women. There's still institutional sexism there, but it's a lot better. Look, in history, only rich white guys could afford to be gentleman scientist. Anyway, we're not talking politics in here. Please turn to your neighbor. Explain the four-step process, and then I'm gonna take a question or two, and then I'm going to excuse you all still early. Okay? Ready, set, go. Turn to your neighbor. 2 minutes.
Yeah. It's stronger.
Oh, which correction? Go. You don't like this? Yeah. To make this reactive. That's like
I get what it's saying. Yeah, that's what I mean, like, what is it?
All right, let's bring it back together. This is probably, in my suspicion, this is the most intellectually complicated single thing in all of physics 111, 112. If you can master this idea, you'll give yourself a big pat on the back. Magnitude and direction of induced current. Questions? Give me a couple of questions, actually. I demand a couple of questions, please. Well, if you can't find the flux, you can't find which way the current needs to be to make it. And if you don't know, if you can't get flux, you don't know the induced voltage. The flux is an intermediary. I don't care about flux itself, but it's needed in order to find induced directions.
Why do we have?
That's where your lights come from. This is how generators work. This is how power plants work. Anything that's not a battery or a solar panel uses this law of physics. Generators, emergency. Yeah.
So for the first step, I just wanna make sure I got it right. Is find and boost current that powers the reactor?
Yeah, next class, I'm gonna teach you how currents make fields.
Okay.
That's previously we've just done right hand rule,
Yeah.
how fields push charges. I'm gonna give you a rule for how currents make fields. Good. Donovan, did you have?
I did, I guess I don't know, I understand the first two, I think the fourth one is like, you're gonna be right, I kind of get what it's saying, but also like in practice, what would it be?
Well, like I just said, I haven't yet taught you how to get field from a current.
Yeah, because what it says works backwards.
Yeah,
Find the closest.
so you don't know the step that you're using to work backwards. Yeah, that's where I'm starting next class.
Okay, then I'm just overthinking.
But once, does it make, do you believe me when I say that if you know how to find field from current, you can work backwards?
Yeah, I get that.
Yeah, it's good. We're good there. Next time. First thing. I demand one more question. Question me one more time. Somebody else. You're not somebody else, but I'll take it. Love your question.
That's a weird thought.
Is flux a what?
Considered similar to time.
If there are tides in fluxes, fluxes going up or down and up or down or not just and down us, then you're gonna be getting increasing voltage. Voltage will absolutely change. Whenever the flux changes quickly, you'll get a big induced voltage. If flux is changing slowly, you'll get, if flux stays constant, you'll get no induced voltage. I'm only ever gonna give you problems, I'm only ever gonna give you problems where the flux is changing steadily. But in general, you betcha, absolutely.
So that is.
And the voltage is constant. Please, last question.
Okay, so for the current, we're talking about when we're working backwards, we're focusing on like how the magnetic field in the third step. Like how it's like, like the opposing stuff, the current creates that magnetic
Yes.
field, okay.
Yep.
Okay.
Okay, I will answer as many questions as you got, but I think that's enough for today. You are all dismissed. You can stick around. But I love you all. Goodbye. Yeah.
Something like that, because when you look at it.
Let me know. I think I'll post it. So there's my exam is tomorrow. But. Microwave.
Yeah, that's like backwards.
I think you're right.
I'm not, I filed next semester, I just have.
Don't. I like it.
I need it for my major, so I would say I kinda have to, but I.
Are you think fundamental or the other one? Or no, microbiome.
I don't, yeah. I haven't.
Because I'm holding the 200, I think, he's only 100.
Number one is.
Either one, like you can use either one. I like mine more than.
I figure it out,
Exactly.
I recently. Sign up.
I love that.
Are you kind of visualizing the feeling that the rest of the program, the sort of field.
Or I'm not like I'm not a mean like. I'm not one of those Pachivos who offended told me in space, so. I don't know, that's just a terminology, and I had a lot of girls in like high school, when they were like, I felt bad, so second, like, I act like a person. Happened way too bit. I think it's suddenly we get to find. Basically one thing as a.
Let me look into that. Okay. I royally. Promise you I had around my fingers by 10. All right, thank you. Oh God, well, I didn't screw it up.
Yeah.
Wait, is it for you too?
I will look into that. Oh, harsh, I'm not on campus tomorrow. Oh, okay, we could still meet, but it'll be online.
Yeah. Absolutely.
Oh, I've got to stop the recording.
How being the